Tonight, we're going to explore why the sky is dark. That sounds like a question with an obvious answer. The sky is dark at night because the Earth has rotated, because we're facing away from our star. You already know this. Everyone does. It seems like it barely qualifies as a question, but that is not the answer. Not even close. The real answer is one of the most mind-bending results in the history of science. It connects the darkness above your head right now, the ordinary, unremarkable blackness of your ceiling and your window and the night outside, to the age of the universe, to the Big Bang, to the structure of space-time, to the death of the observable cosmos, and to a process that is happening right now, tonight, as you lie here. The slow, permanent, irreversible darkening of everything you can see. Here is the actual problem. If the universe contains a very large or infinite number of stars, distributed throughout space in all directions, then the night sky should be blazing, completely, uniformly, in every direction. Every line of sight you could draw from your eye outward into the cosmos would eventually hit a star. Every square millimeter of the sky should glow as brightly as the surface of the sun. There should be no dark patches between the stars, no black gaps, no darkness anywhere in the sky, in any direction, at any time, night or day. And yet the sky is dark. Right now, the room around you is dark. If you were outside, the sky would be black with pinpoints of light scattered through it. Not a wall of fire, not a uniform blaze. Dark. Something is wrong. Something has been wrong with our understanding of the sky since the first person looked up and noticed the blackness between the stars and failed to ask why it was there. The resolution to that wrongness, the full explanation for why the sky is dark, turns out to be not one thing but three. Three separate, enormous, extraordinary facts about the universe, each of them remarkable on its own. Together they dissolve the paradox completely, and in doing so they tell you something about where you are in time, what the universe is doing right now, and what the sky above you will look like in 1 trillion years. By the end of tonight, you're going to understand Olbers Paradox, the 200-year-old question that haunted astronomers for most of the time it was being asked, and that was never satisfactorily answered, until the 20th century gave us the tools to understand the cosmos properly. You're going to understand exactly why an infinite static universe would produce a sky blazing in every direction. And you're going to understand the three specific reasons the sky is actually dark, each of which opens into something larger and stranger than the question itself. You're going to understand what the darkness tells us about the age of the universe, and why the dark sky is direct observational evidence for the Big Bang. You're going to understand how the expansion of the universe is draining the energy from every photon crossing intergalactic distances, and why this makes the sky darker than it would otherwise be. You're going to understand the accelerating expansion that is right now, as you lie here, this very night, carrying galaxies across our cosmic horizon and removing them from the observable universe forever. And you're going to understand where this is all going. The darkness is increasing, the observable universe is shrinking, and eventually, so far in the future that the word eventually loses its ordinary meaning, the night sky will be completely, perfectly, permanently black. Not a single photon from outside our galaxy. Just dark, forever. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The question that launches all of this is deceptively simple. So simple it has been asked by children. So simple it seems like it should already have a clear answer. Why is the sky dark at night? Not why does the sun go down? That's rotation. That's obvious. But why, when you look at the night sky, is it mostly black? Why aren't the spaces between the stars bright? Why isn't every direction you look filled with starlight? In a universe that contains stars in essentially every direction you could point, why isn't the sky a solid blaze of light from horizon to horizon? This question, pursued seriously, turns out to be one of the deepest questions in cosmology. And the people who pursued it seriously, over 3 centuries, from the 1600s to the 20th century, discovered, step by step, that the answer revealed the fundamental nature of the universe, its age, its geometry, its expansion, and its fate. The question has been lurking in astronomy since at least 1576. Thomas Digges, an English mathematician and astronomer, was one of the first thinkers to seriously argue that the universe might be infinite in extent, filled with stars scattered throughout all of space without limit. He immediately noticed that this created a problem he couldn't fully resolve. If stars extended infinitely in all directions, why was the night sky dark between them? He noted the problem. He did not answer it. The question appeared again in 1610 when Johannes Kepler, who had given us the laws of planetary motion, and who understood perfectly well that the stars were other suns at enormous distances, asked directly, if the universe is infinite, filled with an infinite number of stars, why don't we see a star in every direction we look? Why is there darkness between the stars at all? Kepler's answer was that the universe must be finite. There are not stars in every direction because the universe has an edge. Beyond the visible stars, there is a dark shell, a boundary to the cosmos. This was Kepler's resolution. It was an answer. It was not the right answer. Edmund Halley of Halley's Comet addressed the problem in 1720 with a different argument. He pointed out that stars farther away appear fainter in proportion to the square of their distance. So even in an infinite universe, stars at greater distances contribute less light individually, and perhaps the total sky brightness from all these faint distant stars remains finite. This sounds promising until you do the calculation carefully. While any individual star at greater distance is indeed dimmer, there are also vastly more stars at that distance. The number of stars at a given distance grows as the square of the distance, the same factor by which the individual brightness falls. These two effects cancel exactly. The total brightness contributed by all the stars at a given distance band is the same regardless of how far away that band is. In an infinite universe with stars distributed throughout, every distance band contributes equally, and summing infinitely many equal contributions gives an infinite result. Distance saves nothing. Halley's resolution did not work. The problem became formally famous under the name Olbers Paradox in 1823. The German astronomer Heinrich Wilhelm Olbers wrote a careful paper on it, noting the impossibility of a dark sky in an infinite stellar universe and proposing a solution. Space is filled with absorbing material, clouds of dust or gas, that blocks the light from distant stars. Enough absorption, and the accumulated starlight from the most distant sources never reaches us, keeping the sky dark. This was a reasonable hypothesis. It was wrong. The reason it fails is thermodynamic. In a truly infinite, truly static, truly ancient universe, any absorbing material would absorb so much starlight that it would eventually reach thermal equilibrium with the stars around it. Dust heated to stellar surface temperatures would itself glow just as brightly as the stars it was absorbing. The absorption merely converts the blinding starlight into equally blinding thermal radiation from the dust. The sky remains blazing. Blocking does not help. The problem lingered. For 3 centuries, it sat in the literature as an acknowledged embarrassment, a question that pointed to something fundamentally wrong in astronomers' picture of the universe, but that nobody could quite pin down. Every proposed resolution turned out to have a fatal flaw. The paradox was real. The sky was dark, and the universe, as astronomers understood it through most of this period, large, ancient, static, filled with stars, should have produced a blazing sky. Something was missing. The first person to come close to the correct answer was not an astronomer. It was a writer. Edgar Allan Poe, in 1848, in a long prose poem he called Eureka, a philosophical, cosmological meditation that most literary critics dismissed and most scientists ignored, wrote the essential insight: if the succession of stars were endless, the background of the sky would present a uniform luminosity. The only way to comprehend the voids which telescopes find in innumerable directions would be by supposing the distance of the invisible background so immense that no ray from it has yet been able to reach us. Poe understood the universe might not be infinitely old. If stars have only existed for a finite time, then light from stars beyond a certain distance has not yet had time to reach us. The sky is dark because we are looking at a young universe, not an infinite one. Beyond a certain distance, the light has simply not arrived. The darkness is the absence of light that has not yet traveled far enough to reach us. The universe is not old enough for its own light to have filled the sky. Poe wrote this in 1848. He was 70 years ahead of the cosmological framework that would explain why. He died the following year, in 1849, before any of the observational foundations for his intuition were in place. The full answer came from the 20th century, from Alexander Friedman's 1922, Derivation of an Expanding Universe from Einstein's Equations of General Relativity, from Georges Lemaitre's 1927 paper, proposing that an expanding universe implied a past moment of extreme density, a beginning, from Edwin Hubble's 1929 observational confirmation that distant galaxies were receding from us, their light redshifted, the universe measurably expanding in real time, from the 1964 detection of the cosmic microwave background by Arno Penzias and Robert Wilson, the faint thermal glow left over from the early hot universe, the direct observational confirmation that the universe had a beginning in a state very different from today, and from the 1998 discovery that the expansion was accelerating, that dark energy was pushing galaxies apart faster and faster, with consequences for the darkness of the sky that Olbers could never have imagined. When the full picture was assembled, the answer to Olbers' paradox turned out to involve not one fact, but three. Three separate reasons the sky is dark. We will go through each in detail, because each of them is extraordinary, and each of them, when you understand it fully, changes the way you see the darkness above you. But first, we need to understand exactly what the problem is. Why, precisely and mathematically, would a certain kind of universe produce a blazing sky? Imagine standing inside a large hollow sphere. Inside the sphere are light bulbs distributed throughout the interior, equally spaced. Each bulb is the same brightness. The bulbs far away from you are individually dimmer. Light falls off with distance, but there are more of them in the thin shell at that distance, proportionally more, and the two effects cancel. The total light reaching you from bulbs in the near shells equals the total light from bulbs in the far shells, which equals the total light from all shells at all distances. If the sphere is infinite, if there are infinitely many shells of bulbs in every direction, the total light is infinite. Your eyes, immersed in this system, would receive an infinite intensity of light from every direction. Every direction would blaze equally. There would be no dark patches. The sky, for all practical purposes, would be a uniform blaze equal to the surface temperature of the nearest stars. This is the paradox. The universe is like that sphere. Stars are the light bulbs. Space extends in all directions. The mathematics says the sky should blaze. The sky does not blaze. It becomes a derelict. The three. The universe is 13.8 billion years old. It began 13.8 billion years ago in the event we call the Big Bang. Before that moment, or rather, at that moment, because the concept of before may not meaningfully apply, there was no space, no time, no matter, no light, no stars. The universe had a beginning. This is the single most important fact in cosmology. And it is the primary reason the sky is dark. Light travels at a finite speed, approximately 299,792 kilometers per second. This is extraordinarily fast by any human standard. A photon of light crosses the diameter of the Earth in about 43 milliseconds. It crosses the distance from Earth to the Moon in about 1.3 seconds. It crosses the distance from Earth to the Sun in about 8.3 minutes. These are fast journeys. But the universe is not the size of the solar system. It is not the size of the Milky Way. It is vast beyond any intuitive comprehension, and the finite speed of light means that looking out into space is looking back in time. Every photon that reaches your eye has been traveling through space for some amount of time. The photon from the star Proxima Centauri, the nearest star to our Sun, has been traveling for 4.24 years. The photon from the center of the Andromeda Galaxy has been traveling for 2.5 million years. A photon from a bright galaxy in a rich cluster might have been traveling for 5 billion years. A photon from one of the first galaxies detected by the James Webb Space Telescope has been traveling for 13.4 billion years. It left its source when the universe was less than 400 million years old. Before the Milky Way fully assembled, before the Sun existed, before any of the atoms in your body had been forged. But here is the crucial constraint. No photon has been traveling for more than 13.8 billion years, because the universe is 13.8 billion years old. Before 13.8 billion years ago, there were no stars. There was no light. The Big Bang produced the conditions for matter and eventually for stars, but stars did not exist before the universe existed. There is a hard upper limit on how long any photon reaching us has been traveling. The age of the universe. This creates what astronomers call the observable universe. Not the universe, the observable universe. The sphere of space from which light has had time to reach us since the beginning. Because light has been traveling for at most 13.8 billion years, and because the universe has been expanding during that time, stretching the observable volume. The current distance to the edge of the observable universe, the cosmological horizon, is approximately 46.5 billion light-years in every direction. Within this sphere of roughly 46.5 billion light-year radius, approximately 2 trillion galaxies exist. These are the galaxies we can in principle observe. Beyond this sphere, the universe continues, possibly infinitely, but the light from beyond has not reached us. It is on its way, It has been traveling since it was emitted, but it has not arrived. And we cannot see what has not arrived. Olbers Paradox assumed we could see an infinite number of stars, an infinite number of shells of stars at all distances, all contributing equally to the sky brightness. But we cannot. We are limited to the observable volume. 2 trillion galaxies is an enormous number, but it is finite. And the total brightness of a finite number of sources, however large, is finite. The sky cannot be infinitely bright from a finite number of sources. Think of it this way. The grain of sand analogy is often used for the number of stars in the observable universe, and it works in both directions. There are roughly 10 times more stars in the observable universe than there are grains of sand on all Earth's beaches. But the key word is observable. The observable universe has a wall, a horizon, a hard edge defined not by the laws of physics, but by the age of everything. And beyond that wall, the rest of the universe exists, perhaps infinitely, but in darkness from our perspective. Not dark because there are no stars, dark because the star's light has not finished traveling yet. The universe began 13.8 billion years ago, and the light from the most distant sources is still in transit. This alone is the primary resolution. Poe had it in 1848. The sky is dark because the universe is young, because stars have only been shining for a finite time, because light from the most distant stars has not had time to cross the vast space between source and observer. The darkness of the night sky is a direct, observable, undeniable consequence of the fact that the universe had a beginning 13.8 billion years ago. Every time you look up at the dark sky and see blackness between the stars, you are seeing confirmation that the universe is not infinite and eternal. You are seeing evidence for the Big Bang. This is not metaphor. This is not a loose analogy. This is a specific logical deduction. An eternal, infinite static universe would produce a bright sky. The sky is not bright. Therefore, the universe is not eternal and infinite and static. The darkness is the proof. The proof is the darkness. But the finite age is not the only reason. Even with a finite age, the universe contains 2 trillion galaxies with hundreds of billions of stars each. Should not their combined light be enough to noticeably illuminate the sky, even if not infinitely? The sky should be dim from this light, even if not blazing. Something else must be making it darker. And there are 2 more reasons, both of them even stranger than the first. To understand those reasons, you need to understand what the expansion of the universe actually does to light. What happens to a photon that travels across billions of light years of expanding space? What it looks like when it arrives, compared to how it looked when it left? The answer to this is one of the most beautiful and melancholy facts in all of physics. When a photon of light is emitted from a distant galaxy and begins its journey toward us, it starts out with a certain wavelength, a certain color, a certain energy. A photon emitted as blue light has a short wavelength and high energy. A photon emitted as red light has a longer wavelength and lower energy. The wavelength determines everything about what the photon is and what it can do when it arrives. As the photon travels across billions of light years of space, the space itself is expanding. The universe is growing. The distance between any 2 points in the universe increases over time. And as the photon travels through this expanding space, its wavelength is stretched along with the expansion. The wavelength grows. The energy falls. A photon that started its journey as blue light arrives as red light. A photon that started as infrared arrives as radio waves. The expansion of the universe drains the photon of its energy, continuously, over the billions of years of its journey. This is called cosmological redshift, and it is the second reason the sky is dark. The universe is expanding. This was established beyond any serious dispute by Edwin Hubble's 1929 observations, which showed that distant galaxies were receding from us, moving away, and that the recession velocity was proportional to their distance. The further away a galaxy, the faster it was receding. This is Hubble's law. It means that every galaxy in the universe is, on average, moving away from every other galaxy. Not because the galaxies are flying through space in all directions, though some are, but because space itself is expanding. The fabric of space-time is stretching. The galaxies, embedded in this stretching fabric, are carried apart by the expansion, whether they are moving or not. As space expands, photons traveling through it have their wavelengths stretched proportionally to the amount the universe has expanded during their journey. A photon emitted when the universe was half its current size arrives with twice the wavelength it started with. A photon emitted when the universe was 1/10 its current size arrives with 10 times the wavelength. The energy of a photon is inversely proportional to its wavelength. Longer wavelength means lower energy. So a photon that arrives with 10 times its original wavelength carries 1/10 of its original energy. This is not a small effect for cosmologically distant sources. The most distant galaxies visible to the James Webb Space Telescope, galaxies at redshifts of Z equals 10 or higher, have had their light stretched by a factor of 11 or more. A photon emitted as ultraviolet radiation by a star in one of these galaxies arrives at our detectors as infrared or even microwave radiation, carrying 1/11 or less of its original energy. For the most extreme sources, the energy reduction is a factor of 50 or 100 or more. These photons are not contributing meaningfully to the visible brightness of the sky. They have been so thoroughly drained by the expansion that their energy is essentially undetectable without the most sensitive instruments ever built. There is a related but distinct effect. The expansion of the universe not only stretches individual photons, but also stretches the time between successive photons from a given source. If a galaxy is receding from us, the photons it emits arrive at a slightly lower rate than they were emitted, because each successive photon has slightly further to travel than the previous one. The galaxy appears to emit photons more slowly than it actually does. This is a time dilation effect, and it reduces the apparent luminosity of a distant galaxy beyond the simple inverse square law reduction from distance alone. For a galaxy at redshift Z equals 1, moderately distant by cosmological standards, the apparent luminosity is reduced by a factor of 4 from distance alone. With the redshift energy loss and the time dilation, the reduction is a factor of 16. For a galaxy at redshift Z equals 2, the reduction is a factor of 81. These are enormous reductions. Galaxies that are intrinsically as luminous as the Milky Way, but located at cosmological distances, contribute almost nothing to the visible sky. Think of it like sound from a train moving away from you. The pitch drops, the wavelength stretches, not because the train is producing different sound, but because each successive compression in the sound wave has further to travel before reaching your ear. The train hasn't changed. The space between you has grown. Now imagine that same effect operating across billions of light years, applied not to sound but to light, and operating for billions of years of travel time. The light from the most distant galaxies arrives not just quieter but transformed, shifted so far in wavelength that it is no longer even visible. The train's whistle has dropped below the threshold of human hearing. The galaxy's light has dropped below the threshold of human vision. Add up all the photons arriving from all 2 trillion galaxies in the observable universe, after accounting for distance, redshift, and time dilation, and you get the cosmic optical background, the total integrated visible light emission of all galaxies. This has been measured. It is real. It is approximately equivalent to 10,000ths of the brightness of the full moon, spread uniformly across the entire sky. It is completely invisible to the naked eye. It is far below the threshold of human visual detection. The 2 trillion galaxies are there, producing light, sending it toward us. And the combined effect of all that light reaching us after crossing billions of light years of expanding space is so thoroughly diminished by the expansion that it is invisible. The expansion is doing something profound here. It is converting the energy of photons into the kinetic energy of the expansion of space itself. When a photon is redshifted from blue to red, the energy it loses goes into the expansion, not into heat, not into anything detectable, into the expansion of space. The universe is using the light of the stars to fuel its own growth, diluting and redshifting and draining the cosmic light field even as the stars pour energy into it. The result is a sky that should be moderately lit by the integrated light of 2 trillion galaxies, but is instead essentially black because the expansion has drained the photons before they arrive. This effect is distinct from the finite age effect we discussed earlier. The finite age limits the number of stars we can see. The redshift effect limits how much energy each photon delivers. Both are necessary to explain the observed darkness. Together they give us a sky that is dark not just because we cannot see infinitely far, but because even what we can see has had its light diluted to near invisibility by the expansion of the universe during the billions of years of transit. To put real numbers on this, the cosmic optical background, the integrated light of all galaxies, has been measured at approximately 2 to 3 nanowatts per square meter per steradian. 1 nanowatt is 1/1000th of a watt. A steradian is a unit of solid angle. The sky has about 12.57 steradians total. This means the total light from all 2 trillion galaxies integrated across the entire sky delivers less energy to your eyes than a candle at the distance of several kilometers. In a universe with 2 trillion galaxies producing energy at rates that dwarf anything on the scale of planets and civilizations, the total light budget arriving at your eye from all external galaxies combined is less than what you would receive from a birthday candle at the far end of a large building. The expansion has done that to the light. The expansion has taken the collective output of 2 trillion galaxies and reduced it, by the time it reaches us, to something your unaided eye cannot detect. But there is still a third reason. And the third reason is the one that is happening right now, tonight, in real time. A process that is not static or historical, but active and ongoing, making the sky darker every year, every century, every millennium. The process that will eventually isolate us completely, remove all other galaxies from our observable universe, and leave the future of the cosmos in permanent darkness. The expansion is accelerating, and that acceleration is changing everything. In 1998, 2 independent teams of astronomers made one of the most unexpected discoveries in the history of physics. Both teams were studying Type Ia supernova, a specific class of stellar explosion used as standard candles in cosmology because their intrinsic brightness is well calibrated, allowing astronomers to calculate their distances precisely by comparing their apparent brightness to their known luminosity. By studying supernovae in very distant galaxies, both teams expected to measure how much the expansion of the universe was slowing down over time. The physics seemed straightforward. The universe is filled with matter. Matter has gravity. Gravity pulls things together. Gravity should be putting a brake on the expansion. The expansion should be slowing. It was not slowing. It was speeding up. The distant supernovae were dimmer than they should have been if the universe were decelerating. They were farther away than the deceleration model predicted. The universe was not slowing its expansion. It was accelerating. Some force, some energy was pushing space apart faster and faster. This force was named dark energy. It constitutes approximately 68% of the total energy content of the universe. Its properties are unlike anything else in physics. Unlike matter, which dilutes as the universe expands, dark energy maintains a roughly constant density as space grows. As more space is created by the expansion, there is more dark energy in proportion. The more dark energy there is, the more acceleration it drives. The expansion feeds on itself. Saul Perlmutter, Brian Schmidt, and Adam Rees received the Nobel Prize in Physics in 2011 for this discovery. The consequences for the darkness of the night sky are direct and immediate. There is a boundary around us called the cosmological horizon. It sits approximately 46.5 billion light-years from Earth in every direction. Within this sphere, the observable universe exists. 2 trillion galaxies, containing more stars than there are grains of sand on all Earth's beaches combined, and multiplied by 10, producing light that has been traveling toward us for up to 13.8 billion years. Beyond this horizon, the universe continues, but the light from beyond has not reached us. The horizon is the limit of what we can currently observe. But the horizon is not static, and the acceleration of the expansion is changing its character in a fundamental way. Because of dark energy, there is now a specific distance, the Hubble sphere, currently about 14.5 billion light-years, within which galaxies are close enough that the expansion between us and them is slower than the speed of light. Within the Hubble sphere, photons emitted by galaxies can make progress toward us faster than the expansion is carrying the galaxies away. Outside the Hubble sphere, the expansion between us and a galaxy is faster than light. Photons emitted by galaxies beyond the Hubble sphere are currently losing ground. They are moving toward us at the speed of light, but the space between us and their source is expanding faster. They will never arrive. This means that galaxies beyond the Hubble sphere are already unreachable. Their future light will never arrive at Earth, no matter how long we wait. These galaxies are not beyond the observable universe. We can still see their past light, the light they emitted when they were closer to us, and the expansion was not yet fast enough to prevent photon transit. But their present and future is forever beyond our reach. We will never receive news from them again. We are already isolated from their future. As the acceleration of the expansion continues, more and more galaxies will cross this threshold. The Hubble sphere, the region within which photons can still make progress toward us, is itself growing, but not fast enough to include all the galaxies currently within our observable universe. Over time, the number of galaxies from which we can receive new information decreases. Galaxies cross our event horizon, the boundary of what we can ever observe even in the infinite future, and disappear from observability. This is already happening. Right now, tonight, as you lie here, galaxies are crossing our cosmic event horizon and vanishing from the observable universe. Not disappearing physically, not ceasing to exist. They exist in their own regions of space, their own stars burning, their own planets orbiting, their own possible inhabitants, if any, going about whatever they go about. They are as real as they ever were, but their light, emitted from this moment forward, will never reach Earth. The gap between us is growing faster than light can close it. The information they send is chasing us through space and will never arrive. For all observational purposes, for all scientific and practical purposes, these galaxies are gone from our universe. The sky is darkening as a result, not noticeably on human timescales. The change over a single human lifetime is immeasurably small. But it is real. The cumulative loss of galaxies across billions of years is enormous. In 2 trillion years, an almost incomprehensibly distant future, the Milky Way and its bound companions will have merged into a single giant galaxy, sometimes called Nilkomeda, in honor of the Milky Way and Andromeda merger that will occur in about 4.5 billion years. This merged galaxy will sit alone in an expanding, darkening void. The sky from within Nilkomeda will have no external galaxies visible. No Virgo cluster, no Coma cluster, no Perseus supercluster, no light from any galaxy beyond our own. Nothing. The cosmic microwave background will have been redshifted to such long wavelengths that it will be undetectable by any instrument built from ordinary matter. The cosmic optical background, the faint glow of all external galaxies, will have faded to zero. An astronomer in Nilkomeda, looking out at the sky in 2 trillion years, will see only their own galaxy. The rest of the universe, containing everything we can currently observe, will be dark and invisible. Not destroyed, not gone, just unreachable, just silent, just dark. And here is the thing that makes this truly unsettling. That should keep you awake in the way the title promises. Future astronomers in Nilkomeda, if they develop cosmology and physics independently, will have no way to know the universe is larger than their galaxy. All the evidence we use today to understand the cosmos, the recession of galaxies at cosmological distances, the large-scale structure of the universe, the cosmic microwave background, the hydrogen line emission from distant gas clouds, the correlation functions of galaxy clustering, all of it will have been erased or made undetectable by the expansion. Those astronomers will look out and see a dark sky outside their galaxy, and they will have no reason to think anything lies beyond. They will construct a model of the universe in which their galaxy is everything. They will be wrong, and they will have no way to know that. We are lucky. We exist at a time when the universe is still observable, when the CMB still glows, when 2 trillion galaxies can be seen with our telescopes, when the evidence of the Big Bang is still readable in the sky. This window is finite, it is closing, and once it closes, it will never reopen. The darkness of the night sky is not the same thing as empty space. This distinction is subtle and important, and almost always overlooked. When you look at the black regions between the stars, you are not looking at nothing. You are looking through space that is full of things, full of dark matter, invisible, massive, distributed throughout the universe in a vast cosmic web of filaments and halos, making up approximately 27% of the total energy content of the universe. Full of the intergalactic medium, extremely diffuse hydrogen gas, mostly ionized, spread through the voids between galaxies at densities of roughly 1 atom per cubic meter of space, but present throughout the enormous volumes of those voids. Full of cosmic rays, high-energy particles, mostly protons, accelerated by supernovae and neutron star mergers, and quasar jets, streaming through intergalactic space at velocities approaching the speed of light. Full of gravitational waves, ripples in space-time produced by merging black holes and neutron stars across the universe, stretching and squeezing space at amplitudes so small they require instruments kilometers long to detect, but real and present in every cubic centimeter of space at all times. And full of light you cannot see, The cosmic microwave background fills every cubic centimeter of space with approximately 400 photons. Right now, in the volume of your body, roughly 70 liters, 0.07 cubic meters, there are approximately 28 million cmb photons passing through at any given moment. They are moving at the speed of light in all directions. They are photons, real electromagnetic radiation, with a well-measured blackbody spectrum, at a temperature of 2.725 Kelvin. They were emitted 380,000 years after the Big Bang, when the universe first became transparent. They have been traveling since then, 13.4 billion years, redshifting all the while, cooling from 3000 Kelvin to 2.725 Kelvin over that time. They are the oldest light in the universe, and they are passing through you right now, billions per second through every square centimeter of your body, depositing no detectable energy, triggering no sensation, producing no effect whatsoever on your biology. The darkness around you is saturated with the oldest light in existence, invisible because it has been redshifted far beyond the range of human vision. Beyond the CMB, there is the cosmic neutrino background. Neutrinos decoupled from the rest of matter even earlier than photons. About 1 second after the Big Bang, when the universe cooled below the temperature at which neutrino-producing reactions could proceed. These relic neutrinos have been streaming freely through the universe ever since, effectively unobstructed, because neutrinos interact through the weak nuclear force only and can pass through light years of lead without being stopped. The universe is now filled with approximately 336 relic neutrinos per cubic centimeter, about 300 in each of 3 neutrino flavors, plus their anti-neutrino partners. They have a temperature of approximately 1.95 Kelvin, slightly colder than the CMB because they decoupled slightly earlier and cooled further in the subsequent expansion. They pass through you, through the Earth, through the Sun, through stars and galaxy clusters, without pausing, without interacting, without leaving any detectable signal. The darkness around you contains billions of neutrinos per second, passing through every square centimeter of your body. Photons from the afterglow of creation. Gravitational waves from the most violent events in the universe's history. The invisible scaffolding of dark matter. The thin gas of the intergalactic medium. It is not empty, it is saturated. It is full of the invisible remnants and products of 13.8 billion years of cosmic history. The darkness is not the absence of things. It is the absence of things your eyes can detect. And the specific wavelength of electromagnetic radiation that your eyes can detect, visible light from roughly 380 to 700 nanometers, is a narrow and specific band. The universe emits across the entire electromagnetic spectrum, from radio waves hundreds of meters long to gamma rays smaller than an atomic nucleus. In most of that spectrum, the universe is not dark at all. The radio sky glows with the synchrotron radiation of relativistic electrons spiraling in galactic magnetic fields. The X-ray sky blazes with the hot gas of galaxy clusters and the accretion disks of active black holes. The microwave sky glows uniformly with the cosmic background radiation. Only in the narrow band of visible light, the band your biology evolved to detect, because it is the band most abundantly produced by a G-type star like the Sun, is the sky substantially dark. This is not cosmic silence. This is a mismatch between the universe's preferred frequencies and your eye's sensitivity. The universe is extremely loud, in electromagnetic terms. You are just tuned to the wrong station for most of what it is broadcasting. And even in visible light, the sky is not truly dark. There is the zodiacal light, sunlight scattered by interplanetary dust, faintly visible as a glowing cone rising from the horizon after sunset in very dark locations. There is air glow, the faint luminescence of Earth's upper atmosphere from chemical reactions driven by solar ultraviolet radiation. There is the integrated light of the Milky Way's billions of stars, forming the familiar band across the sky. There is the light of individual stars, bright enough to navigate by. And there is the cosmic optical background, the integrated visible light from all external galaxies, too faint to see individually, too faint even to see as a collective glow, but measurable with sensitive photometers as a faint, uniform brightening of the sky above and beyond all other sources. None of this is nothing. The darkness is full, but the fullness is invisible. And the invisible fullness tells you, if you know how to read it, the complete history of the universe, from its first second to the present. Before the universe was dark, it was not dark. There was a time, the first 380,000 years, when the universe was opaque. Not dark, opaque. There is a difference, and it matters. In the first fraction of a second after the Big Bang, the universe existed at temperatures and densities beyond any analogy in human experience. The temperature was measured in trillions of Kelvin. At those temperatures, matter and energy were continuously interconverted. Photons spontaneously created particle-antiparticle pairs. Quarks existed freely, not bound inside protons and neutrons. The universe was a quark-gluon plasma, the most energetic state of matter achievable, and it was blazing with electromagnetic radiation at every wavelength. Photons were produced constantly. Photons were absorbed constantly. The universe was a sea of photons so dense that they could not travel more than a tiny fraction of a millimeter before being scattered or absorbed and re-emitted. Everything was in thermal equilibrium. Everything was at the same temperature. And that temperature corresponded to a luminosity so far beyond any modern astrophysical object that there are no useful comparisons to make. This universe was not dark. It was the opposite of dark. It was the most intensely luminous environment that has ever existed. But the luminosity was not in any direction. It was everywhere, equally, in all directions. The universe was a perfect black-body radiator at an extreme temperature. And the sky, if sky means anything in such an environment, would not have appeared as a dark background with bright sources. It would have appeared as pure, undifferentiated isotropic radiation. Everything the same temperature, everything the same brightness, in every direction. Pure, featureless, blinding light. As the universe expanded and cooled, the quark-gluon plasma condensed. Quarks bound into protons and neutrons. This happened at about a millionth of a second after the Big Bang, when the temperature fell below a few trillion Kelvin. Protons and neutrons bound into helium nuclei. This happened between about 3 minutes and 20 minutes after the Big Bang, in the process called Big Bang nucleosynthesis that produced about 25% of the universe's mass as helium-4. The temperature fell further, but the universe remained opaque. The reason it remained opaque was the free electrons. Electrons in the early universe were not bound to nuclei. The temperature was still too high for neutral atoms to be stable. Free electrons scatter photons extremely efficiently. A photon encountering a free electron is almost certainly deflected, its direction randomized, its journey interrupted. A universe full of free electrons is a universe full of fog, impenetrable in every direction. No photon can travel more than a short distance before being scattered. No structure is visible. No signal can propagate. The universe is opaque. This state persisted for 380,000 years. For nearly 400 millennia after the Big Bang, the universe was a glowing, opaque, featureless plasma. The temperature was dropping. It fell from trillions of Kelvin in the first second to about 3,000 Kelvin at 380,000 years. The temperature of a dim red star, the temperature at which hydrogen atoms become stable. And at about 380,000 years, the temperature fell below the ionization energy of hydrogen. Electrons and protons combined to form neutral hydrogen atoms. The free electrons disappeared, bound into atoms. The fog lifted. The universe became transparent for the first time. The photons that had been trapped in the opaque plasma were suddenly free. They streamed outward in all directions, unimpeded for the first time. And they have been streaming ever since. 13.4 billion years, expanding and cooling with the universe. Redshifting from 3,000 Kelvin visible and infrared light to the 2.725 Kelvin microwave radiation we detect today as the cosmic microwave background. The CMB is those photons. The light released at recombination, 380,000 years after the Big Bang, still traveling, still filling the universe, still telling anyone who can detect it that there was a moment of transition from opaque to transparent, a moment that we call recombination, and that we have detected and measured and mapped with extraordinary precision. After recombination came a period that cosmologists call the cosmic dark ages, a period lasting roughly 100 to 200 million years, during which the universe was transparent. You could see through it, but there was nothing to see. No stars had formed yet. The universe was filled with neutral hydrogen and helium gas, dark matter, and the freely streaming CMB photons, but no sources of visible light. The temperature was still dropping. The gas was cooling. The dark matter was slowly clumping under gravity, building the gravitational potential wells that would eventually draw in the baryonic matter and ignite the first stars. But the stars had not yet ignited. If there were any observer in those cosmic dark ages, which there were not, because there were no planets, no chemistry, no biology, no observers, that observer would have found themselves in a universe that was transparent but utterly dark, invisible light. The CMB would have been detectable as a microwave background, slightly warmer than now. But invisible light, nothing. No stars, no galaxies, no light, just dark matter and neutral gas, cooling, clumping, falling together under gravity in the darkness. Then, roughly 100 to 200 million years after the Big Bang, the first stars ignited. Massive stars, tens or hundreds of times the mass of the Sun, forming from the collapse of primordial hydrogen and helium clouds that had been concentrated by dark matter gravity. These stars were hot, blue-white, enormously luminous. They lived fast and died young, only a few million years for the largest. They produced ultraviolet radiation so intense that it ionized the surrounding neutral hydrogen gas, creating expanding bubbles of ionized plasma in the neutral background. As more and more stars formed, these bubbles grew and merged. The process of reionization, the second time the universe became ionized, this time by starlight rather than by thermal energy, completed over hundreds of millions of years. By about 1 billion years after the Big Bang, the universe was fully reionized. The hydrogen between galaxies was mostly ionized. The universe was transparent again, this time lit by an increasingly rich population of galaxies, quasars, and other luminous structures. The sky had gone from blazing opacity to transparency, with no sources to lit transparency with abundant sources. The Stelliferous era, the age of stars, had begun. And we are still in it. The darkness of the night sky is observational proof of the Big Bang. This is not a metaphor or a rhetorical flourish. It is a specific logical argument, and it is one of the cleanest and most accessible arguments in all of observational cosmology. The argument has the structure of a reductio ad absurdum. Assume the universe is eternal, that it has existed for an infinite time, that stars have always been shining. Then Olbers' argument goes through. The sky should be blazing. The sky is not blazing. Therefore, the universe is not eternal. It had a beginning. Something changed. The stars started shining at a finite time in the past. That finite beginning, combined with the finite speed of light, means we can only see stars within a finite distance. The distance light has had time to travel since stars began shining. Beyond that distance, there are no photons from stars that have yet reached us. The sky is dark in those directions because no signal from those stars has arrived. This argument is available to anyone, anywhere, anytime the sky is clear. You need no telescope, no detector, no training, no equipment of any kind, just eyes and the willingness to notice that the sky is dark between the stars, and to ask why. From that single observation, available for free to every human being who has ever existed, a careful thinker can derive. The universe is not eternal. The universe began. The universe is expanding. The expansion redshifts and drains distant light, and the expansion is accelerating, removing more of the universe from observability every year. All of that from the darkness between the stars. The fact that the sky is dark at night is the most important and most accessible observation in the history of cosmology. Kepler noticed it and concluded the universe must be finite. Olbers formalized it and failed to correctly explain it. Poe intuited the right answer in 1848 without the cosmological machinery to prove it. And eventually, the 20th century provided the proof. The Big Bang, the expansion, the acceleration, the full picture of a universe that began and is evolving and will end in a very specific, very dark, very cold way. We are at a privileged moment in cosmic history, not the center of the universe. There is no center, not the most important location. There is no most important location, but a privileged time. We exist approximately 13.8 billion years after the Big Bang, during the stelliferous era, when stars are still burning across the full extent of the observable universe. When the CMB is still detectable, when the expansion has not yet carried all external galaxies beyond our horizon, when the evidence for the Big Bang is still fully available in the sky and in our instruments. In 100 billion years, none of this will be true. An astronomer in Milkomeda, the merged galaxy that will result from the collision and merger of the Milky Way and Andromeda galaxies over the next few billion years, will look out at a dark sky with no other galaxies visible. The CMB will have been redshifted to radio wavelengths undetectable by instruments built from ordinary matter. The cosmic optical background will be gone. The large-scale structure of the universe, the filaments and voids of the cosmic web that allow us to measure the expansion today, will have been wiped from observability by the recession of the galaxies that constitute it. That future astronomer, developing physics and cosmology from scratch, will have no reason to think the universe is larger than their galaxy. They will be wrong, and they will have no way to discover their error. We are not in that position. We live when the evidence is still there, when the universe is still observable. When the question of why the sky is dark can be asked and answered with reference to real data and real physics. This is a gift, not a gift in a sentimental sense, but in the literal sense, that it is something we have that future observers will not have. The observable universe is, For any given observer, a diminishing resource. It shrinks over time as the acceleration of expansion removes more and more from view. Future observers will see less. We see more than they will. And we see less than observers a billion years ago would have seen. The window of observability is open. It will not stay open. And what we learn through it, about the Big Bang, about the expansion, about the dark energy driving the acceleration, about the ultimate fate of the observable cosmos, is knowledge that, once lost to the receding horizon, can never be recovered by observation alone. The cosmological horizon, the boundary of the observable universe, is approximately 46.5 billion light-years from Earth, in every direction. This is the current distance of the sources of the oldest light reaching us. It is a sphere. We are at the center of that sphere, not because we are special or privileged in position, but because any observer anywhere in the universe is at the center of their own observable sphere, the sphere of space from which light has had time to reach them since the beginning of the universe. The horizon is not fixed, it is evolving. And the evolution has two competing aspects that together determine whether the observable universe is growing or shrinking. On one hand, as time passes, light from more distant sources has more time to reach us. In 1 billion years, we will have had 1 billion more years for light to travel. So in principle, we should be able to see 1 billion more light years into the universe. The horizon should be growing. On the other hand, the acceleration of the expansion is carrying distant sources away from us faster and faster. Sources that were once receding slowly enough for their light to still make progress toward us are now receding so fast that new photons from them will never arrive. The set of sources from which we can receive new information is shrinking. Which effect wins depends on the rate of acceleration. With dark energy as currently measured, a cosmological constant with a constant energy density, the acceleration wins in the long run. The event horizon, the boundary of what we can ever observe even in the infinite future, is currently located at approximately 16 billion light-years from Earth. Any source currently beyond 16 billion light-years is already beyond our event horizon. Any light those sources emit from this moment forward will never reach us. We can still see their past, the light they emitted when they were closer, before the expansion had accelerated to its current rate. But their future is permanently hidden. The event horizon is smaller than the observable universe, much smaller. The observable universe is 46.5 billion light-years in radius. The event horizon is about 16 billion light-years in radius. Most of what we can currently see is already beyond our event horizon. The light we currently receive from those sources left them in the past, when the expansion was slower. The present state of those sources, what they look like right now, is information we will never receive. They have already sent their last message. We just haven't read it yet, because light travels at a finite speed. As the acceleration continues, the event horizon grows slightly, because the universe continues to expand, bringing in a slightly larger volume of space from which at least some past light can reach us. But the overlap between our current observable universe and future observability shrinks dramatically. Galaxies that are currently observable, that we can see in our telescopes right now, are being lost to the event horizon over time. Their future light is already beyond our reach. In a few billion years, even the light currently in transit from the most distant observable galaxies will have arrived, and no new light from those sources will follow. They will go dark. The sky darkens one galaxy at a time, on timescales of billions of years. Right now, tonight, the sky is marginally darker than it was a million years ago. Not detectably so. The change per million years is immeasurably small. but cumulatively, over billions of years, the change is enormous. The sky is dimmer than it was during the quasar epoch, approximately 10 billion years ago, when active galactic nuclei outshone entire galaxies, and the intergalactic UV background was at its peak intensity. The sky will be dimmer in 10 billion years than it is tonight. And in 2 trillion years, it will be darker than anything we can currently imagine. The darkness of a universe in which the sky, from within the sole surviving galaxy, contains no external light at all. Tonight is a good night. Tonight, the sky above you has 2 trillion galaxies. Some of them are as close as a few million light years. Some are 46 billion light years away. All of them are contributing, however minutely, to the photon field of the universe. The cosmic optical background fills the sky at a level just below human visual detection. The CMB fills every cubic centimeter of space with its ancient microwave glow. The universe is present in every direction, in every wavelength, in every particle streaming through the darkness. This is the most observed night in the history of the universe for us. Not the brightest. The universe was brighter in the past, and will be brighter still from other vantage points. But for us, here, in the Milky Way, at this moment in cosmic history, this night represents the full extent of everything we can see. Everything that will ever be observable to us is either already visible or currently en route. In the future, that list will only shrink. Look at the darkness tonight, if you can, and know that it is full. Full of photons you cannot see. Full of galaxies too distant and redshifted to make visible light. Full of the CMB, the oldest light in the universe, the afterglow of creation. Full of dark matter and dark energy, the invisible architecture and the accelerating force. Full of neutrinos from the first second of the universe's existence. Full of gravitational waves from the most violent events in cosmic history. And know that it is darkening. Slowly, imperceptibly, irrevocably. The stelliferous era, the age of stars, will end approximately 100 trillion years from now, when the last red dwarf star burns out. 100 trillion years is 10,000 times the current age of the universe. We are very early in the stelliferous era. The universe, from the perspective of stellar evolution, is young. Most of the stars that will ever exist are either burning now or will burn in the future, because the smallest red dwarfs can sustain nuclear fusion for trillions of years. But the era ends. The gas runs out. New stars cannot form without fresh hydrogen. The hydrogen is being locked away in stellar remnants, white dwarfs, neutron stars, black holes, where it cannot be recycled into new stars. Over trillions of years, the pool of available star-forming gas depletes. The star formation rate declines. The last stars form. The last stars burn out. After the stelliferous era, the universe enters what Fred Adams and Greg Laughlin, in their landmark 1997 paper on the long-term fate of the universe, called the degenerate era. The universe is populated by stellar remnants, white dwarfs, the compressed carbon-oxygen cores of former stars like the Sun, supported against gravity by electron degeneracy pressure, slowly cool toward absolute zero. Neutron stars, the even denser remnants of more massive stars, supported by neutron degeneracy pressure, also cool more slowly. Black holes of all sizes, from stellar black holes a few times the mass of the Sun to the supermassive black holes at the centers of former galaxies, persist, the only structures that are not cooling and fading. The sky from within a galaxy at this era, from within the remnant that used to be the Milky Way, would be extraordinary in its emptiness. No stars burning. The remnants of old stars slowly cooling, growing dimmer and dimmer. The most recently formed stars, the last red dwarfs, burning for trillions of years, cooling from red to infrared to microwave, eventually becoming what Adams and Laughlin called black dwarfs, cold, dark, inert carbon-oxygen spheres, former stars, completely black, emitting no detectable radiation. The sky would be black, except for the faintest thermal glow of the coolest, most recently dead stars. And the CMB would still be there, fainter, more red-shifted, cooler, but still filling every cubic centimeter of space with photons. Photons from the recombination epoch. 380,000 years after the Big Bang. Still traveling, still cooling with the expansion. At 100 trillion years after the Big Bang, the CMB temperature would be approximately 0.003 Kelvin, 1,000 times cooler than today. The photons would have wavelengths of centimeters rather than millimeters. Still real, still present, still the afterglow of the Big Bang, just impossibly cold and impossibly faint. Then, if proton decay occurs, as predicted by some but not all grand unified theories, the white dwarfs and neutron stars and the rocky remnants of planets would dissolve over timescales of 10 to the 34 to 10 to the 40 years. Protons, the fundamental building blocks of atomic nuclei, would decay into lighter particles. Positrons, photons, pions, the matter we are made of, the matter stars are made of, the matter planets are made of, would dissolve. White dwarfs would turn to a diffuse glow of positrons and photons. The remnants of Earth, by this point a cold, dark, rocky remnant orbiting a cold, dark white dwarf, would dissolve into radiation. If proton decay does not occur, if protons are stable, white dwarfs persist indefinitely as black dwarfs, cooling forever, but never dissolving. Either way, by the end of the degenerate era, the universe is either populated by black holes and diffuse radiation, or by black holes and cold black dwarfs, and cold rocky planetary remnants. In a universe so vast and so cold and so dark that the concept of a sky barely applies to any meaningful observer. Then, the black hole era. The only significant structures remaining are black holes. And black holes, through the quantum mechanical process described by Stephen Hawking in 1974, slowly evaporate. The Hawking radiation process is extraordinarily slow for large black holes. A stellar mass black hole of 10 solar masses requires approximately 2 times 10 to the 67 years to evaporate. A supermassive black hole of 1 billion solar masses requires approximately 2 times 10 to the 83 years. TON 618, the most massive confirmed black hole at 66 billion solar masses, will evaporate in approximately 10 to the 99 years. These numbers are so large that the current age of the universe, 13.8 billion years, is effectively zero by comparison. To make this concrete, if you wrote out the number of years until TON 618 evaporates in full, 10 to the 99, the number would contain 100 digits. The age of the universe contains 11 digits. The ratio between those two numbers is larger than the number of atoms in the observable universe. The black hole era dwarfs everything that has come before it in the history of time. During the black hole era, the universe's sky, from any hypothetical vantage point, though there would be no observers, would be essentially completely dark. The only light produced would be the Hawking radiation from black holes. Thermal radiation at temperatures so close to absolute zero that even the longest wavelength radio detectors would struggle to measure it. For a stellar black hole, the Hawking temperature is approximately 60 billionths of a Kelvin. The Hawking radiation from a supermassive black hole is at a temperature of billionths of a Kelvin. These are not just cold. They are the coldest temperatures that physics can produce in a physical system. The sky during the black hole era would be dark at every wavelength to any conceivable instrument. And then the black holes themselves evaporate, one by one, over incomprehensible timescales. Each evaporation ends in a burst of Hawking radiation, the final moments of a black hole, as it shrinks to a size where the Hawking temperature becomes measurable, and then explosive, and then complete. A brief flash of gamma rays and particles, and then gone. After the last black hole evaporates, somewhere around 10 to the 100 years after the Big Bang, there are no more structures. The universe contains only photons, electrons, positrons, and neutrinos, spread at the most extreme dilution across a universe so vast that adjacent particles might be separated by distances larger than the current observable universe. This is the dark era, maximum entropy, the heat death. A universe in perfect thermodynamic equilibrium with no gradients, no processes, no change, no observers, no information. Just the expansion of space, carrying the last particles farther and farther apart, the temperature falling toward absolute zero but never quite reaching it, the photons redshifting toward infinite wavelengths and zero energy. The darkness that began as a cosmological puzzle, why is the night sky dark when the universe contains stars, ends as the ultimate state of the universe. Not dark because of the finite age and the redshift and the acceleration. Dark because everything has evaporated. Dark because there are no more sources. Dark because entropy has done its work. The universe began in unimaginable brightness and density. It will end in unimaginable darkness and diffusion. The darkness of tonight's sky is a temporary, local, historically specific state on the road from the blazing beginning to the silent end. We are somewhere in the middle. The sky is dark between the stars because the beginning was 13.8 billion years ago, and the expansion has been stretching and draining the light ever since. And the sky will be darker still, darker and darker and darker, over timescales that dwarf human comprehension, until there is nothing left to make it bright. The universe is dark, and the darkness connects to the other two great facts about the universe that this channel's trilogy of Reason videos has explored. The universe is empty. 95% of its energy content is in forms we cannot see, dark matter and dark energy. Of the ordinary matter that exists, the average density across the observable universe is approximately 6 protons per cubic meter of space. A cubic meter of air contains roughly 25,000 trillion molecules. A cubic meter of interstellar space contains, on average, a few million hydrogen atoms. A cubic meter of intergalactic space contains fewer still, perhaps 1 atom. The universe is overwhelmingly void, with tiny concentrations of matter, planets, stars, galaxies, floating in an enormous, nearly empty sea of space. The emptiness explains part of the darkness. Even with 2 trillion galaxies producing light, the photons must cross such enormous volumes of nearly empty space that the probability of any given photon hitting your eye is vanishingly small. The sky is dark, partly because the universe is mostly empty. The universe is silent. The Fermi Paradox, the question of why we have not detected signals from extraterrestrial civilizations, despite the universe containing billions of potentially habitable worlds, has the same underlying explanation as Olbers Paradox. The finite speed of light, the vast distances, the finite age of the universe, and the accelerating expansion that is carrying potential communicators beyond our event horizon all contribute to a silence that is not necessarily permanent, but is real and profound. We are in a universe where communication is limited by the speed of light, where distances are so vast that even the nearest stars are years of light travel time away, and where the expansion is actively reducing the number of sources with which communication is in principle possible. The silence is the same universe as the darkness. Empty, silent, dark, three faces of the same cosmos. A universe that began with a Big Bang 13.8 billion years ago that has been expanding and cooling ever since. That is accelerating in its expansion. That has a finite observable region that is shrinking over cosmic time. And that is moving, step by irreversible step, toward the maximum entropy state of the dark era, where nothing moves, nothing shines, nothing signals, and nothing is there to ask why. We are in a fortunate position, not permanently fortunate, not special in any cosmic sense, but temporarily, locally, historically fortunate. We exist at a time and place where the universe is still accessible, where it can be observed and understood and questioned, where the darkness of the night sky can be noticed and interrogated and turned into knowledge about where the universe came from and where it is going. The question, why is the sky dark, led to the Big Bang. It led to cosmic expansion. It led to dark energy and the accelerating universe. It led to the cosmic horizon and the shrinking observable universe. It led to the heat death and the ultimate fate of everything. All of that from the darkness. All of that from lying here in the dark and wondering. The universe is dark for a reason. The reason is the age of the universe. The reason is the expansion. The reason is the acceleration. The reason is the physics of space-time and thermodynamics and the way entropy always increases and never decreases. And the reason is exactly what should keep you awake, not with terror, not with existential dread, but with wonder. The darkness above you right now is evidence. Evidence for the beginning of everything. Evidence for the expansion that is carrying the galaxies apart. Evidence for the dark energy that is accelerating that expansion and darkening the sky in increments too small to measure, but too real to ignore. Evidence that you are here, in the middle of the universe's active phase, in the bright window between the opaque beginning and the dark end. In the brief cosmic moment when the night sky contains 2 trillion galaxies and the CMB still glows and the Big Bang's echo is still detectable. We are the universe noticing itself. Every question asked about the darkness, every measurement made of the CMB, every redshift recorded from a distant galaxy. Is the universe developing the capacity to examine its own nature and trace its own history? The atoms in your body were forged in stars that lived and died before the sun existed. The oxygen you are breathing right now was synthesized in the cores of massive stars that exploded as supernovae, scattering their contents across the galaxy, which eventually became part of the molecular cloud that collapsed to form the solar system. You are the product of stellar nucleosynthesis and planetary accretion, and 4 billion years of biological evolution. You are, in the most literal possible sense, the universe assembled into a configuration capable of asking why the sky is dark. And the answer is the universe itself, its age, its expansion, its acceleration, its beginning, its end. Tonight we asked why the sky is dark. We followed the question past the obvious answer, past rotation, past the setting sun, all the way down to the 3 reasons that actually explain it. The universe had a beginning. 13.8 billion years ago. Stars did not exist before that. Light from stars beyond a certain distance has not had time to reach us. The observable universe is finite. The darkness is, in part, the darkness of the time before stars existed, visible as the boundary of what light has had time to cross. The universe is expanding. Every photon crossing the billions of light years between distant galaxies and our eyes is stretched by the expansion, its wavelength lengthened, its energy drained. The light of 2 trillion galaxies arrives at our detectors after being reduced by factors of hundreds or thousands, drained of energy by the expansion that stretches every photon during its journey. The darkness is, in part, the darkness of light that arrived with almost no energy left. The universe is accelerating in its expansion. Galaxies are crossing our cosmic event horizon and disappearing from the observable universe forever, one by one, over timescales of billions of years. The sky is growing darker. Not tonight's sky relative to last night's, but this century's sky relative to 1 billion years ago. And definitely this era's sky relative to the far future, when the acceleration will have carried all external galaxies beyond observability and left our descendants in permanent darkness. The darkness is evidence. The darkness is data. The darkness of the night sky is the most important and most accessible observation in the history of cosmology, available to anyone anywhere for free on any clear night. And it tells you, the universe began, it is expanding, it is accelerating, and it will end in cold, dark silence. Right now, outside your window, the sky holds 2 trillion galaxies. The cosmic microwave background fills every cubic centimeter of space with 400 photons from the moment the universe first became transparent. The cosmic neutrino background, from 1 second after the Big Bang, passes through your body in billions per second. The dark matter halo of the Milky Way extends hundreds of thousands of light years in every direction. Dark energy fills the vacuum of space, pushing everything apart, darkening the sky by increments, accelerating the future darkness. And the sky looks black between the stars, not because there is nothing there, because what is there has been stretched and drained and dispersed by 13.8 billion years of expansion. And because the light from what lies beyond has not yet arrived, and because more of what lies beyond crosses our horizon every year and falls into permanent unreachability. The darkness is the universe's autobiography, written in the absence of light, told in the gap between the stars. You understand it now, what it is, why it is, where it came from, where it is going. The sky will be there in the morning, slightly darker than it was 1 million years ago, slightly brighter than it will be 1 million years from now, still full of galaxies, still full of ancient light, still full of the evidence of everything. There is a version of you that will close their eyes tonight and see only darkness. But you know what that darkness contains now. Every cubic centimeter of the air around you is threaded with 400 photons from the moment the universe first let light travel freely. Every second, billions of neutrinos from 1 second after the Big Bang pass through your body. The gravitational waves from merging black holes in distant galaxies are right now, this moment, stretching and compressing the space between your atoms by a distance smaller than a proton. The dark matter halo of the Milky Way flows through the room around you, invisible, undetectable, but present. Hundreds of thousands of light years of dark matter scaffolding, anchoring the galaxy that contains the star, that warms the planet, that grew the organisms that became you. The darkness is not absence. The darkness is everything. It is the full history of the universe, compressed into the space between the stars, readable only if you know what to look for. And now you do. The universe is dark for a reason. The reason is the Big Bang, the expansion, and the acceleration of everything away from everything else in an irreversible race toward maximum entropy, maximum distance, maximum dark. And somewhere in that dark, on this small planet, orbiting this ordinary star, in the outer arm of this unremarkable galaxy, at this precise and fleeting moment in the life of the cosmos, something the universe assembled from ancient starlight is lying here, in the dark, wondering why. The answer is the universe itself. It always was.